going to talk about receivers now, and in the question bank there's receiver block diagram and receiver operation, but what I'll just talk about the two together because they're fairly inextricably linked. Receivers are ubiquitous. They're in everything we do in radio, really. They form a critical function. Every piece of gear we have, be it the smallest handheld transceiver or more sophisticated high-frequency, including VHF, UHF sets such as this. Of course, we've all got receivers that allow us to receive the signal that someone's sending to us or something we want to listen to. Normally, a receiver and a transmitter will be combined together in the same box called a transceiver, and often sharing quite a number of functional blocks to do that. But people will still operate receivers on their own. For instance, maybe a scanning receiver that has a number of memories programmed into it or can search over a wide range of frequencies that you might want to listen to, emergency services and or air traffic, that kind of thing. You might have a separate high-frequency receiver in your Radio Shack if you want to listen to other bands while you operate on another one or something along those lines. Some people still operate a separate receiver and a transmitter. That was common in days gone by, probably up until the 1970s. You could buy separate transmitters without a receiver in it, and you had to operate the two together. That's not done as often, but the vintage people often will do that. And shortwave listeners, people who like to listen to shortwave radio stations or listen in on amateur traffic as well, will use a separate receiver. So we're just going to talk about receivers in general. It doesn't matter if it's combined with a transmitter and a transceiver or a separate unit on its own. They still operate the same. Receiver has a fairly difficult job, actually. It's just what we want a receiver to do is remove the modulation, the intelligence from a carrier, although a single sideband, that carrier can be suppressed, but you get the idea. We want to remove the intelligence off of the radio signal and be able to listen to it or do something with it, listen to it on a loudspeaker or headphones. If it's data, we want to be able to remove that intelligence, feed it to our station personal computer or what have you, and display text information that's been sent in packet radio or other data modes or radio teletype. Or listen to Morse code, produce beeps in response to pulsed radio carriers, as in continuous wave signals. So that's what we want them to do. They have a fairly tricky job because the signals coming in down our antenna feeder, our transmission line, are incredibly weak. Some can be very strong. The amateur across town will be coming in at maybe 1 billion times stronger than a weak signal we want to hear from the other end of the country or the other side of the world. So you have to be able to receive weak signals. They also have to be able to cope with quite strong signals not on the frequency we're listening to, but maybe nearby and can cause problems. Nearby in frequency, I mean. And so there's certain qualities to be able to listen to a weak signal, but at the same time reject other signals that we don't want to listen to. So I thought we should just start with the most basic receiver. It's not actually in the question bank, so you don't have to learn this particular part, but it's of interest just to get us started. The most basic receiver historically has been the crystal set, or crystal receiver. And I think if we just start on this one, it just shows some of the principles that we'll be using a bit later on. And these were originally built to listen to AM signals, that is a full carrier with upper and lower sideband attached, and did it simply and cheaply. Now a crystal receiver is basically based around two things: a tuned circuit, which we learned about in resonance, a parallel tuned circuit, which we attach an aerial to. There's our symbol for an aerial, and an earth. So we've got, in effect, a generator, if you like, applied to the tuned circuit between the one side connected to ground, the other side connected to a wire outside, an antenna. Generally the capacitor was variable, but in some of the old days, sometimes the inductor was made variable. Now, Remember, a parallel tuned circuit has its highest impedance at resonance. So if we tune this to the station we want, for instance, Radio Marlborough is a local AM station around 1600 kilohertz or 1.6 megahertz. If we tune it to that, it will have a very high impedance, a high AC resistance, if you like, across the tuned circuit at that frequency, and low at other frequencies. So any other signals we don't want tend to just go disappearing through the tuned circuit down to ground, but the signal we want at that particular frequency will be not affected and will be appearing across that tuned circuit, and that's what we'd use a tuned circuit to do. We tune it to resonate at the frequency we want to receive. Now, remembering that an AM signal has that appearance, remember the AM envelope, the carrier wave superimposed with the modulating signal, so that can be the modulating signal there, the intelligence, just a straight sine wave, maybe a tone. If it was music or speech, it would be more complex looking than that, but it will do for the explanation. So what we want to do is be able to remove the intelligence off of the carrier. So we've tuned the signal we want, that's what we've got at this point here, and enter our friend the diode from semiconductors. Remember, the diode would only allow a current to pass in one direction and not the other. And that allows us to detect or demodulate, to get the intelligence off of the carrier signal. So the first step we do, just like when we come on to power supplies in a bit, we've now removed our the other half of the signal, if you like, and now we're left with this pulses of carrier and the general shape of the intelligence. And that's what's at this point here. And what we do is put a fairly small capacitor to ground. Now, the fact that we've gone to ground here means that symbol means ground. It can be the metal box that perhaps we build this thing in, and these two points are attached together by wire and connected to the ground. So that symbol means that they're connected to the same thing, which is the ground. What that capacitor does there is it charges up between bursts of carrier. So, right, my pen's falling apart here. So that's the carrier there. We get this effect here. So we recreate our audio signal, if you like, off the AM signal. We remove the other half, and what we've done with the carrier, the capacitor can just charge up between bursts of carrier, and then we end up with, another thing is it's doing is it's filtering off the carrier wave, redraw it. We end up with this, our original audio signal. Very weak, but if you're listening to a fairly strong local station, there's some symbols for some headphones. There's enough signal power there to hear on headphones without any sound amplification at all. This thing runs without batteries. It's what we call passive. So a tuned circuit, diode detector, a filtering capacitor to get rid of the carrier, and some headphones. Pretty simple, really. They won't work very well. They're not very loud. Although if you've got a strong broadcast station within a mile or two, a few kilometres, it will be loud enough that when you take them off, you might be able to hear it from a little way away. But not that loud, not room-filling audio anyway. One of the problems with these, so that was really the first, or one of the first types of receivers. The reason they called it crystal was because silicon diodes and germanium diodes weren't around back in the 1900s, 1910s, and often they used a piece of lead sulfide crystal, galena, and if you had a little fine wire, you could shift it around the surface of the crystal and find a point where it would rectify or detect. And that was where the cat's whisker terms come from. It was a little fine wire that stuck onto it. Life's a bit easier these days, isn't it? It's the crystal set. The basic receiver, it suffers from several big problems. One, it's not very sensitive. There's no amplification in it, so things don't sound very loud, and certainly weak signals are a problem for them. The other main problem with them is selectivity. That's an important receiver property we'll talk about again in a little bit, but receiver selectivity is really the ability of your receiver to tune, to listen to, if you like, tune to the signal you want, And signals that are a bit above or a bit below in the frequency spectrum to that wanted one, we don't hear them. So we can select the one we want, but not hear other stuff, especially close in. That's called selectivity. The crystal set, just having that one simple tuned circuit, is not very selective. If you've got two strong AM signals in town, within a few miles from your home, you'll have a job separating the two. You'll often hear them both together, or you tune to one and you'll hear the other one weaker in the background. So it's not exactly high performance stuff, but at least it got the radio world started. The next one, and once again this isn't examinable, was what's called the tuned radio frequency, TRF. And I think it's useful to mention this particular type of receiver as a jump between the basic crystal set and the super heterodyne receiver, which we'll be talking about shortly, the definitive receiver really that we deal with nowadays. The tuned radio frequency came about with the invention of the vacuum tube, the valve, which allowed amplification of radio signals. And the idea was that you had an aerial. We'll just draw it as a block diagram, okay, here. So we had a tuned circuit, if you like. Just draw that a little bit better. Well, let's just say a tuned amplifier. So we use that triangle symbol for an amplifier. So a tuned circuit and a valve amplifier in one functional block. And then generally a second or even a third. And then we'll just draw the crystal detector there and off to our headphones. It would have had the diode, the capacitor as well to filter out the carrier. It might have also had another amplifier after that detector operating at audio frequencies, down at sound frequencies, down at a few kilohertz, just to amplify it up enough to operate a loudspeaker so you could fill a room with sound. I did mention one or more tuned circuits. Generally what they did was two or three tuned amplifiers. The idea of doing that was that if you draw kind of a curve with perhaps the frequency that our receiver was tuned to here, and we could do this very crudely and just maybe the loudness of the signal in our headphones. And the idea was that whatever we tuned to would be the loudest, and stuff that we weren't interested in, so that might be Radio Marlborough on 1600 kilohertz. So the national program over in Wellington down here about 567 maybe was still hearable, but and then some marine traffic up here, or maybe 2182 kilohertz, you wouldn't want to hear that. So with one tuned amplifier, we'd still be perhaps maybe able to, still stuff either side, or especially closer in, we'd be able to hear it, which wasn't much good. When you actually put a second tuned amplifier in, you actually tend to sharpen the response up, so you get more like this. You see you're starting to leave out this other stuff, and then by the time you put in a third, things are becoming much more selective. You're able to select what you want. But there's a few problems with these receivers. One was a bit tricky to adjust. You had to have three. So we've put an adjusting arrow in here just to show that the tuned circuits and that can be adjusted. They had to be mechanically tied together so that all three would track together. You didn't want to have all the three capacitors in there all mounted together on the same shaft, because then you get feedback problems. You'd have a very strong signal here by the time it's got this far, feeding back to the tuned circuit in that one, and the thing the set would oscillate, which is not what you wanted to do. Often they had to have maybe three separate tuning knobs in a row, and you had to tune them to all three at the same point. They worked, but it was a bit fiddly. The other thing too is, as you tune over that wide frequency range, the curve naturally changes, just the way that tuned circuits work, so it might be more selective at the 1600 kilohertz end, but not as selective down the bottom. But at least it put us on the path to be able to have some amplification in the system to receive weak signals, and to have better selectivity. And then in the 1920s, Edwin Armstrong, American researcher, I think he had a military rank, came along and invented, it's got a great name. Back in those days, things often had these great prefixes, super this and heterodyne, and there was the super het. No, second try. If I had a director, you know, and a camera operator, we could just cut. The super heterodyne receiver got around a number of these problems, and by making things, you know, quite a bit more complex, but it really got around the selectivity problem. And how it does that is, and the stability too. Remember I said you could get feedback problems with that kind of layout. That's what we call stability, by the way, or one of the big factors that influence stability is the fact that the receiver will sit there and function nicely without misbehaving itself. The other factor to do with stability is whether or not it will stay tuned to the point we want it to, and we'll come on to that in a minute when we talk about local oscillators. The idea of the super heterodyne receiver was to have a lot of amplification in your receiver, but to do it at one fixed frequency where all those tuned circuits could be preset and set up to give a nice selective receiver, but shift the frequency we want to receive to that frequency, and we call that an intermediate frequency. So we receive our signal we want, which you often call the RF, the radio frequency, and then we shift it to the IF, the intermediate frequency, which can be anything. It can be quite low, a few tens of kilohertz, and some receivers right up to quite high, maybe 70 megahertz or so in that Yaesu set I showed you before. And it uses the technique of heterodyning, or well, I don't know if you can call it that, heterodyning, but the idea that you can actually use two signals and combine them together and shift them to a third point. And I think a good example to illustrate this is if we have we want to operate a receiver in the 80 metre amateur band at 3.5 to 4 megahertz range, and we use what's called a 9 megahertz intermediate frequency. So we'll just start in the middle. We have in here an IF, or intermediate frequency amplifier. So it's an amplifier that's designed to work around the frequency we want. In this case, it'll be 9 megahertz. And what we did, sorry, I just had to edit that bit out. I hope you can't hear in the background. There's a dog having a good howl. The local town pound is just over the back fence. He's obviously not happy, he or she. Okay. Now what we do to control the selectivity of our receiver, and what we do in modern receivers, in days gone by, what the IF amplifier would contain several amplification stages, transistors or valves, and each stage had a tuned circuit built into them, tuned to the intermediate frequency amplifier, a bit like the TRF thing, but all at one frequency. Nowadays what we tend to do is use an IF amplifier, which is, it might be a bit broad, it will amplify other frequencies as well. But to make it narrow, to make it selective, there's a filter put in front of it. Here's the way the signal's going. A band pass filter. There's a symbol for a band pass filter. It won't pass frequencies above the frequency you want it to pass. It will. It hasn't got a line through it for the middle one, and the frequencies below it's got a line through it. In other words, it's a filter with a response like this, and ideally it's pretty sharp like this. So, for instance, if it's centered on 9 megahertz, it will just pass a little bit above, a little bit below, but outside that range, nothing. It's just like a window on the radio spectrum, if you like, that's just as wide as we want it to be. Now, if it's a single sideband signal, only about 2.5 kilohertz, because that's all we want to get through there. It's just, that's all we tend to transmit when we use SSB, like we discussed with modulation. For frequency modulation, we come on a bit, that would be wider to pass the FM carrier that's been wobbled around in there. So we put a filter in front of there. Normally, we talked about filters back in resonance. We showed you a crystal filter or two. We'll show you, we show a real receiver in a little while. This is generally done with crystal units in a little package. So now we've got a functional block that will amplify things at a frequency, at one fixed frequency, and just that, around that frequency, and nothing above or nothing below. Now, we'll talk about single sideband in a minute, but if it's an AM receiver, we'll have our diode and capacitor combination, and then into an audio frequency amplifier, because now we're not at 9 megahertz, we're down at sound level, and a loudspeaker. If it's an AM receiver, then this would have to be wider again. It would have to be wide enough to pass the lower sideband, the carrier, and the upper sideband. So there you are. That's the sort of the tail end, if you like, the back end of an AM super heterodyne receiver. If we want to receive an amateur signal on 3.5 megahertz, this isn't going to do it on its own, is it? It'll receive a 9 megahertz signal, but won't receive 3.5. So we have to shift. The idea of this is we want to shift our signal at 3.5 megahertz to 9, where we can do the bulk of the signal processing, if you like, filtering, amplification, detection. So what we do is we have our aerial here with our 3.5 megahertz signal, kicking the telephone over on the floor, and we generally, but not always, but put a radio frequency amplifier in here just to provide a bit of amplification at the start of the receiving process. And the reason we do this is that signals here can be very weak. They can be just above the noise level, the background noise level that's generated in maybe the feed line from the antenna and so on. It's a bit more academic down at 3.5 megahertz, where atmospheric crashes and static and rubbish and lightning strikes all around the world, and Pacific anyway, will certainly dominate things. But as we get up into the higher bands, like the 20 meter, 14 megahertz band and above, the noise and the rest of our receiver can tend to dominate things rather than atmospheric noise. So it helps just give the signal a bit of a lift at the start before it meets the rest of the electronics, just to get it up above the noise level that's generated later in the receiver. So that's the idea of the radio frequency amplifier. Now we enter a new block symbol there with I draw it like that with a cross in it, and that's a mixer. And we need something else. A little generator here called the local, I think in the NZART question bank it's just called the oscillator, but normally in super heterodyne receivers we call it the local oscillator. You can draw an arrow there just to show which way the signals are going. This is what we call the front end of the receiver. And the function of this part of the receiver is to shift the signal we want to receive to the intermediate frequency, where we can do the filtering and the bulk of the amplification. Mixing, the mixer, that's an interesting device. It can be just the simple diode arrangement like that will do the job, or field effect transistors, dual gate FETs operating in a particular way, or a bunch of 4 diodes and a couple of transformers will do it. You can read more about that if you're interested in how they work. But a mixer is a device which has got 2 ports, often called the local oscillator and the RF port, and then an IF port where the signal, where the output is. What a mixer does, and we normally use the thing called the double balance mixer here. A mixer takes 2 signals, the radio frequency signal, which we can call F frequency 1, and the local oscillator frequency 2, and it combines the 2 together to give an output which is the frequency 1 and 2 added together, and then the difference between them. What's called the sum and the difference. So coming out of here is F1 plus F2 and F1 minus F2. Just put the bigger in front of the smaller. So what if we make this 5.5 megahertz? If our local oscillator, now the local oscillator is actually a signal generator, if you like, inside our receiver. It's an amplifier which has got a tuned circuit built into it, making it feed back on itself and produce a nice, generally, hopefully a sine wave at that particular frequency at 5.5 megahertz. Nothing else, we just want 5.5 megahertz. Now F1 plus F2, 5.5 and 3.5, added together, 9 megahertz. Okay? And the difference, but the other what if we subtract the 2? 5.5 minus 3.5, it's 5 minus 3, which is 2. So coming out of the mixer, we've got a 9 megahertz signal. We've shifted our wanted signal at 9 megahertz, be it AM or a single sideband or FM or something like that, whatever we're set up to receive at the far end of the receiver down here. And there's also a 2 megahertz signal, You can see what happens. The 9 megahertz signal will just go through the filter like it's hardly there. It will suffer a bit of, it will lose a little bit of signal, only a decibel or so, but not much. Then amplified tremendously by the intermediate frequency amplifier, many millions of times, and then hit the detector, changed to an audio signal, and through the audio frequency amplifier to give it the final lift to a sound level. Only a little bit of the amplification is done in RF amplifier. The audio frequency amplifier does a bit more than the RF amp, but much less than this. The bulk of it's done at the intermediate frequency amplifier point. And the filter in front of it, the combination of these two, will only allow what we want to pass through. So if there's a signal at 3.6 megahertz, which there often is on the amateur band, 3.6 plus 5.5 is 9.1. We don't want to receive that 3.6 megahertz signal. You can see when it's shifted up using this process, 9.1 won't pass through the filter because it's only very narrow. Okay, 3.55, 50 kilohertz up, that comes through here at 9.05. Still way outside the pass band of the crystal filter. So only till you get signals very, very close in that, remember I drew that nice rectangular shape of the filter. It's not quite perfect, so signals right next door, you will start to hear them. But you can see the idea that we only have to design and build and buy, which these can be quite expensive, these crystal filters. You know, to get refitted ones for your transceivers, they can be up to 150, 200 US, they're not cheap. So we can just put this expensive device at one frequency and use it for all others by shifting when we want to that frequency. And that's the idea of the super heterodyne. Heterodyning meaning frequency shifting. I'm pretty sure that's what it meant anyway. Now, yes, better explain what I meant by double balance mixer. Simple mixers will put, you not only get F1 and F2 coming out there, you'll get F1 plus F2, F1 minus F2, you'll also get F1 and F2. The local oscillator will come out and the RF signal will come out as well. So you get 9, 2 in that example, 5.5 and 3.5. And that's not always helpful. So often better quality receivers will use what we call a double balance mixer, or sometimes called a DBM at that point, at that mixer point. But that's the basic idea of the mixer, to shift the frequency we want to the intermediate frequency using a local oscillator. It's just straight maths. It doesn't know maths, it just happens to do it. It's quite a complicated process going inside there, but we don't need to know about it. I've built receivers like this and I still don't really understand the fancy mathematics involved that's going on, and it's just quite amazing. I'm digressing now. In radio you can get quite complicated things to explain at the most basic levels, but we don't need to know that. We just treat it as a building brick in the system. I'll just come on to one of the problems we have with a super heterodyne receiver, and that's image. The image. Now in this example we're wanting to receive a signal on 3.5 megahertz, so we tune a local oscillator for a 9 megahertz IF. Obviously if the IF was 10 megahertz, that filter there, an amplifier was designed to run at 10 megahertz, we would have to make our local oscillator, what would have to be? 6.5, wouldn't it? That plus that gives 10. Go back to 9. What happens when the amateur across town is, let's find a better example. Let's say across town there's someone running a transmitter on 14.5 megahertz, sorry. I was going to say 20 metres, it's just outside it. Let's say the 20 metre band was a bit bigger, but let's say there's a signal, pardon me, around at 14.5 megahertz as well, quite strong signals coming down the aerial. Doesn't matter where it came from, but that's quite on the cards. Maybe a shortwave station or something like that. There's a bit of a problem here, you see. 5.5 megahertz plus 3.5, okay, will come out here at 9. That's right, we want to receive that one. We also get the difference too, don't we? Not just sum and difference. 14.5 minus 5.5, that's the difference frequency, will come out of here as well, and there's not a thing we can do about that mixer to stop that. That will happen. You can't make a double balance mixer that will suppress, it'll only let the sum or the difference out, but not both. They both come out. So 14.5 minus 5.5 is 9. So the problem with a super heterodyne receiver set up like that, it will always receive two frequencies. It will receive one we want, which is a sum of the local oscillator and the received signal. Will also receive the difference, which is a bit of a pain, isn't it? So we have to do something to stop that. We don't want to receive a 14.5 megahertz signal. There may not be anything there, and that's not a problem, but if there was, we would hear it, and there's not a thing we could do about it. So enter something which is not drawn in the NZART question bank block diagrams, but all receivers will have a filter here. Often a bandpass, doesn't have to be a bandpass filter, but we won't go into all the details. But what we do here is we put a filter right at the very front of the receiver called a bandpass filter. And what we do is it's a filter, it's doing a similar job to this one here, but it's much broader. What we want to do, so if we want to tune the 80 metre band, 3.5 to 3.9 in New Zealand, obviously we have our local oscillator tuning 5.5 to 5.1. Okay, 9 minus 5.1 is 3.9. So we have to make our local oscillator tunable. If we want to receive 3.5 megahertz, we tune it to 5.5, because 9 minus 5.5 is 3.5. If we want to listen to 3.9 megahertz, we tune this to 5.1. 9 minus 5.1 is 3.9. That's how we tune a super heterodyne receiver. So I should have mentioned that before. We just tune the local oscillator. We make it adjustable to receive whatever frequency we want. Now, to get rid of the image problem, we have to stop the image from getting into the front end of the receiver. This is part of the front end, but we don't want it to get into the radio frequency amplifier, and we don't want it to get to the mixer anyway. So what we do is we put a bandpass filter here. We'll only pass that range of frequencies and reject everything else. So the 14.5 megahertz signal that would get through when we've got the local oscillator tuned to 5.5 to receive 3.5 just doesn't get through the bandpass filter, and we won't receive it. No filter's perfect. It'll always let a little bit through at other frequencies, so if it's super duper strong, then yes, you might hear it, but most of the time we can say it's gone for good and it's not a problem. So you might say, well, hang on, when those bandpass filters expensive things? Well, no, they're not, if we want to make it quite broad. It's not too difficult to make a filter past that 400 kilohertz range, and a couple of tuned circuits. You don't have to know for the exam for this much detail, but we mentioned this in filters and resonance. This kind of arrangement with these two tuned circuits tuned to in a particular way, and the two tuned circuits coupled together with a capacitor like this, this will quite cheaply will pass the particular band of frequency we want. The response curve will be something like this generally, sort of a double hummed arrangement like that, and the sides aren't as steep as a crystal filter we'd use there. They tend to be rolled off a bit. But that's good enough most of the time for the job we want to do. So that's, say, 3.5 to 3.9, and 14.5 is way the heck up there, and it's not having a show of getting through the thing. Well, not unless it's incredibly strong. And that's not an expensive thing to do, although to do it very well can take a bit of design. But so that's the bandpass filter. Just for an interest, in our common garden AM broadcast band receiver, which has to tune 0.5 to 1.6 megahertz, that's a big range. That's a 3-to-1 tuning range, much wider than this. That's only 500 kilohertz. The other one is letting through, you know, a bit over 1 megahertz wide, and it's a big proportion of the frequency receiving. It's a big range with respect to the signals we're talking about. You can't build bandpass filters to do that. And what generally is done in AM broadcast receivers, like your bedside clock radio and things like that, is they actually have a tuned circuit in here doing it, that's adjustable, and it's tied together with this. The tuned circuit, the tuned capacitor here that we're adjusting, the frequency, the local oscillator frequency, will be coupled to the capacitor and the bandpass filter, if you like, and the two will track each other so that this is always tuned to the frequency you want to receive. But that's not commonly done in modern amateur receivers. They'll have a bandpass filter, like I just showed you before. So that's super het receivers, and we put this bandpass filter at the front to reject the image, because the image will be a major problem to us if we. Okay. Just another thing we need to talk about is the frequency we choose the IF to be at, the intermediate frequency to be at. We can, for all intents and purposes, choose any frequency we like. Generally, one of the things we do is we choose at a frequency that we can make a nice narrow filter to operate at. In the early days of receiver construction using super hets, you could only really build a narrow filter IF amplifier arrangement at quite low frequencies, typically only a few hundred kilohertz. And that causes some problems, and we'll just show you why. We'll just illustrate an example. If we want to receive, say in the 15-meter amateur band, a signal on 21 megahertz, and what if our intermediate frequency was quite low, just half a megahertz, or would normally say 500 kilohertz? Then we'd need to, say, have a local oscillator running at 21.5 megahertz. 21, the difference between the two, 21.5 is 0.5 or 500 kilohertz. That's fine, that will work nicely. What if we've got, but unfortunately our image will now be 22 megahertz, because 22 minus 21.5 is that. So it causes a few problems, because the 15-meter band is what frequency? 21 to 21.5 megahertz it runs from. But it could quite easily be a strong broadcast station or some other station at 22, and they're very close together. Okay, they're a megahertz apart, which may sound a long way, but they're still on the spectrum right next door to each other, 21, 22. And it becomes quite difficult to have a filter at the front that can easily allow this one to go through and block that, because as a percentage they're very close together, and that's the key thing with filters. So there you are. There's an obvious problem with having quite a low intermediate frequency. In the early days of receivers, that was quite a problem. Well, not up until about when these narrow filters were coming in. We're talking up to about the 50s and 60s. So if you had your IF running at a frequency that allowed you to have a nice narrow filter, you had gross image problems. Your image was very close to the frequency you wanted, the signal you wanted, and you had problems with that. So what they used to do, they used to use what was called double conversion. And I'll mention this because it's in the NZART question bank. What they used to do was actually have a first IF, have two intermediate frequencies, just to complicate things. But what they'll do is they'll make the first intermediate frequency quite high. So say we want to receive a 21 megahertz signal. So they'd put the first intermediate frequency at, say, 9 megahertz. Right? Get rid of the IF amp. Put a second mixer, then the filter. I'll just draw this a bit better. Then the IF amp there. Bandpass filter there. I must remember to stop putting the end on the pen. So here we've got our narrow half megahertz, 500 kilohertz filter here, an IF amplifier running at a half megahertz doing most of the receiver amplification. So what you do is you'd start at the first IF of 9 meg, so we'd convert, what's 21 minus 9, that's 12 megahertz. Have our local oscillator running at 12 megahertz. If we wanted to receive 20 megahertz, we'd have it running at 13 megahertz. And then just in front of the 9 megahertz, sorry, no, we've got the filter there. What we did was they put a filter in here, just using simple inductors and capacitors, just a cheap filter arrangement, that would pass 9 megahertz and a bit above and a bit below, but not a lot outside of that range, okay? So it would have a response. It wasn't a super expensive filter with a nice narrow response like that. It would be a bit more like this. Probably quite a bit wider than that. But good enough so that the image wouldn't have a show of getting through there. So because the image would be so far away. So what's the image going to be? The difference between the two, 21 plus 12, 21 minus 12 is 9. The image is going to be 21 plus 12, which is what? 21, 31, 33 megahertz is the image coming out there. Now, it doesn't take much of a filter to stick in here that will pass 9 but not 33. So by having that relatively high intermediate frequency with a relatively El Cheapo filter, we can eliminate our image with that first conversion, if you like, to 9 megahertz IF. And then what we would do is have a second mixer here with an oscillator here running at 8.5 megahertz that would convert the 9 down to 0.5. 9 minus 8.5 is 0.5. This was fixed. This just stayed at 8.5 megahertz because this is that's the first IF, that's the second IF. These don't change. The tuning is done with this one. This was the adjustable one, so to cover over the 21 megahertz band, you'd move that by the same amount that you needed. So that was the idea of double conversion. It was a technology that went out with the availability of nice narrow crystal filters coming in, because then you could put all your selectivity at the 9 megahertz point. You didn't have to down convert to a lower frequency to do all your selectivity. So that double conversion went out, and single conversion was all the rage for a number of years. And now with the more modern, what we call general coverage high frequency transceivers that amateurs use that will cover any frequency you like between say 1.8 and 30 megahertz instead of in particular band chunks. They've gone back to this kind of technology, and maybe we'll talk about that at the finish. But that's a double conversion receiver. It was done primarily in the early days where you could only get your narrow selectivity at a relatively low IF frequency, so they'd put a first IF step ahead of it to reject the image and then down convert to that lower frequency where you could have the selectivity built in. It's called double conversion. Some receivers even use triple conversion, but we won't go into that. But there were a number of problems with this arrangement too. You had multiple oscillators running in your receiver, and numbers of different frequencies being converted to, and that can cause their own problems if you go and read a bit more about receiver design. Also, there's two mixers, and that causes problems as well with strong signal performance. So there were some problems with that arrangement, but it was really the only way it could be done. And just put a reminder there for later. So just sticking with the subject of the straightforward, there's the front end filter, mixer, local oscillator, my pen's getting fatigued, bandpass filter. Sticking back with a straightforward single conversion receiver, what we now need to talk about is how we receive single sideband. That's where things get a little bit more complicated. The front end arrangement is still the same. We still have, if we want to receive 3.5 megahertz, the local oscillator running at 5.5, the mixer, crystal filter here at 9 megahertz, IF, and so on. The problem with receiving single sideband is that there's no carrier there. The demodulation process is not straightforward like we drew before, with just a diode detector stripping off half of the carrier arrangement and then a little bit of filtering, and out comes your audio. The problem with single sideband is that there's no carrier there in the first place to produce sound, so we have to re-inject it. And that's where we add another mixer, generally called the product detector. Hope you can read that, product detector. Then off into the audio amplifier and then the loudspeaker. And then we had another local oscillator here called the carrier insertion oscillator, or the beat frequency oscillator. So, what if we were wanting to receive a lower sideband signal? Now this is what's coming down the area. The carrier's been suppressed, okay? There you go, there's the lower sideband, there's the carrier. 3.5 no longer exists. We've only got this bunch of frequencies just below the carrier, which is our sound from our microphone, if you like, that's been shifted up in frequency, and it's just below. Remember, when it's silent, no one's speaking, there's no energy there. As you talk, if you whistle a single note, there will just be one signal there, a number of frequencies in our voice, there'll be a whole bunch of them. And that's what's coming out at this point here. If we put a single sideband signal into an AM detector with no carrier re-injected, it sounds awful. This is what people used to call duck talk in the old days when they tried to receive single sideband on their AM-only receivers. You got this sort of horrible noise. And what in effect it is just actually the signals within the single sideband signal combining with each other to produce sound signals, and it doesn't sound very nice. You certainly can't understand it. So what we actually do is we use a mixing process to shift our single sideband signal up at the intermediate frequency down to sound. So what we've effectively got coming out the end here, the output of the IF amplifier, is where the carrier should have been at 9 megahertz. Okay, and the sideband. So there's no carrier there, but we've got the sideband a bit above. Things get put upside down because of the way the frequencies are mixed, if you do the maths, but we don't need to go into that. But just suffice to say that coming out of the IF amplifier, there's no carrier, and we've got our intelligence just spread over a range from 9 to just above 9. So if it's a 1 kilohertz tone we're whistling, coming out of there will be 9.001 megahertz. Okay, if we're managing to whistle a couple, but when there's speech, there's a whole bunch of signals there. So what we have to do now is we want to get that 9.001 megahertz tone, whistle, whatever, back down to 1 kilohertz, which is what it originally sounded like when it went into the microphone. And here we use that F1 plus F2, F1 minus F2 process that mixers do. So the product detector, the straight AM detector is just called a detector, but a detector for detecting single sideband is called a product detector. And what we do is we feed 2 signals into it, just like we did here, except we inject in here a carrier, so 9 megahertz, and you've got 9.001, so outcoming here is 1 kilohertz, our original sound signal, and 18.001. Now that's not going to go anywhere. The AF amplifier will just laugh at the this doesn't cause any problems. So we get the sound back coming out the other end. So that's how single sideband receivers work. Whoops, been caught up in my microphone cable. We have the signal that coming out of the IF amplifier, the sideband signal, mixed with our beat frequency oscillator, and out comes the audio that we started off with, our intelligence. Originally called beat frequency oscillator because people used to call combining 2 tones together beating them together. The other term that you'll see called, which I think is more self-explanatory, is carrier insertion oscillator. You're re-injecting the carrier back in and you receive it. This is why single sideband receivers are quite a lot more complicated than just a straightforward AM receiver. An AM receiver, all you need here is a diode detector arrangement and off you go. Single sideband, you have to put a second oscillator in here and a second mixer. This oscillator is generally crystal controlled. It has to be very stable. Otherwise it will cause quite significant problems to the operation of the receiver. If we wanted to receive Morse code, we still have to use the same arrangement, because a Morse code signal is just a carrier, continuous carrier wave, or continuous wave, if you like, of oscillations being switched on and off. So what we do if we want to receive Morse code is we use a similar arrangement. So what we've got now coming out here is an intermediate frequency signal switching on and off. And if we just tune the receiver right, so we've got a bit of a difference between this and that, so we can adjust this here just to get the pitch right as we shift the local oscillator up and down. The relationship will shift between the two, and we can get the tone higher and lower. And that's what old AM receivers used to have. You used to switch on a beat frequency oscillator, which was injected often in just the straight AM detector, and it still worked fine. And then instead of hearing just hearing the carrier wave switching on and off, the two combined to produce an audio tone, and then you hear the dee 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 dee, you know, for CQ, if it was Morse code. Right. So that's single sideband or SSB receivers. If you want to receive the upper or lower sideband, we won't go into all the details, but there's several ways you can go about it. But commonly what we would do is just switch between two carrier frequencies here. So if it was the other sideband, what we could do is inject the carrier at that point there and get the sound out. We won't go into that in all the details. If you want to read more about that, it's quite well explained in all the text. It's just a simple way of just shifting the carrier insertion oscillator. The other thing I want to talk about is different intermediate frequency filters. Really going to have to get a new pen, aren't I? I've already worn out a few of them. I've got another one here. Here we go. Right. The requirements for the filter here in radios that receive different modes, as in single sideband or Morse or AM or so on, we have different filter requirements. If we want to receive AM, we have to be able to fit the upper and the lower sideband signal through. So if the highest speech frequency that's been put onto the AM carrier is, say, 2.5 kilohertz for communications quality, then the filter is going to have to be 5 megahertz wide. Remember that the AM signal is twice as wide as the highest modulating signal. If we want to receive single sideband, typically it's about half that, around 2.1, 2.4, 2.8 megahertz. Because if we make the filter too wide, what will happen is when we tune to a single sideband signal we want to listen to, if we've got a wide AM filter in there, we might hear the SSB conversation a few kilohertz up will get through. So we'll hear two lots, which is a pain. We don't want that. Likewise with Morse code, we've just got one carrier signal for all intents and purposes switching on and off. If we can actually use quite a narrow filter in there, because with Morse code you can stack a lot more Morse conversations up the band quite closely together, and so it's an advantage to use a narrower filter there for Morse code requirements. So what's typically done in receivers is these filters are switched. So there'll be a bank of filters. Often perhaps if you buy the lower specification you'll just get one, but you can, as optional extras, you can get them added in. That one I showed you before, the AC one there, I've got a Morse code filter in that, for those of us that still use it occasionally. So often what you'll have is a switched arrangement there. A symbol shows us that these can be switched in and out. And the receiver, according to how you operate it, will select the appropriate filter you want. So that could be an SSB filter that's, say, 2.4 kilohertz wide. This could be an AM filter that's, say, 5 kilohertz or 6 kilohertz wide. And this could be a CW filter that's, say, 500 hertz wide or even narrower. And that's switchable intermediate frequency filtering, and that's very commonly done these days. And but you do pay extra for them. So we'll just keep it simple. We'll just go back to our one filter there. Right, another feature that we have in receivers, we talk about a number of things so far, is automatic gain control, or AGC. The difference between a weak signal and a strong signal, just talking generally, is incredible. The weakest signal we might be able to receive on the receiver I showed you there before, the ASUS hit, might be only just down to a few tenths of a microvolt. On the 80 metre band that's impossible, because on the 80 metre band the atmospheric noise is much higher than that. There's a lot of static crashes and goodness knows what, so there's no point in making the receiver that sensitive. And the RF amplifier, which I left off, will often be switched out on the lower bands because it's not required, and it actually it can degrade receiver performance in other ways, which we might mention towards the finish. On the higher bands, it's certainly useful to have it there. But the strongest signals might be many millivolts. If you've got a ham just a few hundred metre, a kilometre away like I do, his signals are incredibly strong. So the problem you have is if you want to tune from one to the other, you'll be forever adjusting your volume, your AF gain. I forgot to mention that. Audio frequency gain is the volume control. It just adjusts how much amplification your audio frequency amplifier has. So what we do is we have a block here called AGC. What the AGC is, it's a bit of circuitry that looks at how strong the signal is coming out of either the IF amplifier, or it can be done from the AF amplifier, one or the other. And it just basically is measuring how strong the signal is coming out the back end of the receiver. And if it's incredibly strong, to avoid you getting your ears blown off, what is it on a very strong signal, what it will do is it will feed back generally to the intermediate frequency amplifier. It will turn down how much it amplifies. It will turn down the IF volume control, if you like. And some receivers will also reduce the RF gain as well. But so it's just an automatic system for keeping, in fact it used to be called AVC for automatic volume control, but nowadays we call it automatic gain control. It's a system that all receivers have for all intents and purposes. It just keeps the listening level at a comfortable level. Because the other time it's useful to have is when in fading. We'll talk about that when we come to propagation, but on high frequency signals that have bounced off the ionosphere to get to us, there can be quite significant changes over a short period of time in the strength of the signal over a wide range, and the automatic gain control will cope with that, so we can just leave the receiver running at one particular loudness level, and most of the time the AGC will just keep the volume at a comfortable, well, whatever level we set the volume control at, and it won't change in volume. The design of good automatic gain control systems and better quality receivers is quite sophisticated. They'll have quite fancy systems there to cope with the conditions they're exposed to. When you're receiving AM, it's quite easy because it doesn't matter if anyone's talking or not. There's a carrier there to tell the works how strong the signal is. With single sideband, when you stop talking and the amateur at the other end pauses for a second or so to think about what they're going to say next, maybe the weather or something like that, the receiver will, there's no signal coming in, there's nothing there, we'll just crank the gain right up. And so then when they start talking again, bang, there's often a bit of what we call overshoot. The system takes a bit of time to respond to the signal, so you might get a sudden burst of loudness coming out of a loud sound signal before it brings it back under control. And what single sideband systems will do, will often have a bit of a delay in there, that it will just keep things set as they were for a second or so, maybe just around the second mark, just so you don't get what's called pumping, big changes in the loudness coming out of your receiver with speech going on and off and so on. Right, so that's automatic gain control. We need to talk about frequency modulation, FM receivers. Now, FM receivers share a lot in common with what we've been talking about so far. The difference is the tail end of the receiver is different. We still have a front end, if you like, which is the RF amplifier. Oh, I keep forgetting to put our filter in here. Our front end filter, a bit smaller. Sorry to see on videotape. To get rid of the image. RF amplifier, mixer, local oscillator, main bandpass filter for setting selectivity, and intermediate frequency amplifier. And this is where it gets different. And this is what multi-mode receivers do. What I mean by multi-mode is that they can receive a number of different modulation types. Is often what they have is this part here will be shared by everything. Sometimes the IF can be different, but there's different ways of going about it. But what's connected on the back end is different for AM, for single sideband, for FM. Perhaps we'll leave out this thing called the limiter first. We have a thing called a frequency demodulator. It's called an NZART question bank. Another more common term is discriminator. And that's what removes the intelligence off an FM signal. Now there's a number of different ways you can do that, and all sorts of different techniques. But we won't go into that. We don't need to know that for the exam. But all these systems share something in common, which is that they receive. It's a device which puts out a signal that varies in proportion to the changing input frequency. And often it's a device, not often, it's not always, but a device will have some sort of characteristic like this, where this is the FM carrier signal, so it will be designed to work at the intermediate frequency. So if it's a 9 megahertz IF, and this has a voltage out. And what it does is, as the carrier signal that we're receiving has been frequency modulated, FM, moved up and down, the voltage coming out of this device here, so if the carrier wanders down there, it will be this level. As it wanders down, as it goes up in frequency, it will be that. Down, it will be that. So you can see you're getting a waveform coming out, varying between those two, and it will do it at the rate that the carrier is shifting. And that's the basic idea behind the discriminator or FM demodulator. It's a device that produces a varying voltage in response to a varying carrier coming in. So that will be an audio, that voltage will change just like the audio signal did in the microphone at the transmitting end that moved the carrier. A fairly common way it's done now is using a device called a phase lock loop. Now that's a whole hour class on its own, we won't go into that, but a phase lock loop we'll come back to them at the end of this session when we come back to local oscillators and modern receivers. Now, so that's how we get the sound signal back off the FM carrier. But we have a device in front of it called the limiter, and the limiter is what gives us the sound quality, the interference immunity that FM has. Remember we talked in modulation about how FM's, one of the advantages of using FM is it's quite immune to noise, ignition noise, whatever, say especially receiving in a car. And the reason was that it's not noise is an amplitude phenomenon. If you've got, with time, your FM signal bunching up and spreading out, the signal going up and down, we don't care what the amplitude is of, it's a changing frequency that gives us the information. Now, if you get ignition noise appearing regularly along it, on an AM receiver we'd hear click, 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 we'd detect that off. But we don't need the amplitude information to get the sound off an FM carrier. And what the limiter essentially is, it's an amplifier that goes flat out and drives into what's called clipping. You mentioned that way back in the single transistor amplifier. So no matter what signal, for all intents and purposes, coming into it, the output is clipped off, if you like that. But the information, the frequency changing information is still there, but it's been flattened off. So any impulse noise is just obliterated, it's gone. It's like we've planed the signal clean. But the carrier, the changing frequency is still present. That information is still there, but any amplitude stuff on it is gone, which we don't need. So the impulse noise is gone. So there you are, that's the advantage of the FM receiver. It does fall over. When signals are getting very weak, if you're down to getting down into signal levels that are getting towards the sort of the limits that we can receive on an FM receiver, then things start to get bad because we're trying to amplify the heck out of a very weak signal anyway, and the impulse noise starts to appear on it because we can't amplify it all the way up. The impulse noise starts to sneak through, it doesn't get planed off, and we'll start to hear it. We'll also hear noise generated in the limiter, which is why when you listen to an FM receiver with no signal present, you get that horrible rushing noise, a whole burst of white noise. So we'll just power up this receiver, but it's kept silenced by a squelch. So there you are. When I push the button there, it just turns the silencing system off. And that's what FM receivers sound like when nothing's going into them. They generate all that noise. For the reason just explained, they're amplifying the heck out of nothing, out of the noise coming through anyway, and then you just hear that horrible rushing noise. And what FM receivers is they have a squelch system. Squelch or mute. Now this is not covered in the exam, but I think it'd be madness for us not to mention. The squelch is a block off to the side like the automatic gain control we talked about before. What the squelch essentially does is it monitors the noise level. The better ones do. What they do is they monitor how much noise is coming out of the system. If there's a whole lot of noise, it probably means there's no signal there. So what it does is it operates essentially a switch in the audio amplifier to shut the sound off. When we get a nice clean signal, which we'll hear on the tail of this repeater when we trigger, it's got quite a long tail and it's got a Morse identification code. It says BM, Blenheim in Morse code. And that noise at the end was the carrier dropping out, so the nice clean carrier signal with no noise on it. And just as the works are switching off, you get a bit of a burst of noise coming through as the carrier drops out and the system recognises it's noisy and shuts it down. You'd be very fatiguing listening to an FM receiver all day without that system. So that's a mute, and it's generally adjustable. The more modern handhelds, there's not enough knobs to go around, so often it's preset internally on a menu option. The reason it's adjustable is that if you're in a very high noise environment, it's often the mute will start to open. When I mean noise, like local signals and interference and rubbish, and sometimes you want to actually make the system require a cleaner signal, if you like. I don't know if it's explaining it well, but it is useful to have the threshold, if you like, at which it will allow a signal to come out adjustable. You want it to be have a very high threshold in a very noisy environment, but if you're in the middle of nowhere and you want to listen to weak signals coming from a distant repeater and you're in a quiet, electrically, local noise level, sense, quiet area, then you can make it much more sensitive. Okay, so that's FM receivers. Typically that's at higher frequencies, maybe VHF, that one we're just listening there was 146.95 megahertz we were receiving. The intermediate frequency in those handhelds is often in 10.7 or 21.4 or something like that. So the local oscillator will be running at quite a high frequency, around the 130 odd megahertz range. Just a final comment about FM receivers. Intermediate frequency filter bandwidth. Remember we said that sharp crystal filter we put ahead of the intermediate frequency amplifier. An SSB will be about 2.5 kilohertz, typically Morse code. If we want to have better selectivity, we can go right down to 500 hertz. We can manage with 2.4 or 2.8, but we'll hear a lot of other stuff we don't need. We'll hear maybe a Morse conversation going off quite high-pitched audio, and another one going quite low, which can be quite annoying. Now for FM you need a wider filter again. It depends on the amount you deviate the carrier, but typically for communications quality, 10, 15 kilohertz, you need quite a wide one to fit the frequency shifting FM carrier through. You have all sorts of problems if you make it too narrow. You get quite a lot of distortion of your signal. Your audio will sound terrible. In a TV receiver where you're deviating 50 kilohertz, or a commercial FM at VHF, your 88 to 108 megahertz receiver, that's 75 kilohertz deviation. So you need quite a wide filter in a FM broadcast receiver. Right. Just one last thing we need to come back to. A couple of things. Signal to noise and stability. Not the same thing, but just to remind myself. And there's another few more last things I want to mention that's definitely not in the NZART examination, but I think it's useful to talk about. And I'll just make a note here so I remember. Direct digital synthesis, phase lock loops, they're sort of together. What else do I want to mention? Intermodulation. We'll just call it intermod. I think should do for now. Right, first stability. We talked about selectivity, the narrowness of our receiver filtering, so we only would receive the signal we want and don't have to listen to conversations above and below on the frequency band. We've mentioned image rejection, which when we're using a super het receiver, which is most receivers nowadays, is the property where you have filtering at the front end of your receiver to reject the sum or the difference, the one that we don't want, of the relationship between the local oscillator and the IF and the signal you want to receive. And the other thing is stability. When we're listening to a single sideband conversation, if our local oscillator shifts up or down in frequency a little bit, then the pitch of our received signal will change, and we'll do a demonstration hopefully in another session, watching a receiver in action. You'll hear the pitch going up and down will change as the local oscillator drifts. So that's often nowadays what we refer to as stability in a receiver, is a local oscillator staying where it's put. What you tune it to, it will stay there and won't move in frequency. Signal to noise. Now it's often called signal plus noise to noise ratio, but we'll just call it signal to noise ratio in receivers, and that's covered in the examination. When we've got a signal arriving, here's our receiver. RX is often a symbol for receiver. Hello, I'm getting a bit audio coming out there. It's a symbol for a coaxial plug. The signal that arrives into our receiver from the antenna, there'll be things, well, the signal will be present and there will be noise present. And we can draw it on a graph, if you like this. So here's perhaps frequency up there. That's the strength of the signal, or the voltage of the signal arriving. And if it's a very, very strong signal, we'll just draw it as one line, a single sideband. We don't have to, let's say it's a Morse code signal when the key's down, so it'll just be continuous carrier. Now, coming in through the terminal, there'll be the signal we want, but there'll be noise. And you can draw it as sort of this random stuff, distributed up and down in frequency, all the way down to very low, way up to very high frequencies. Now that noise is coming from a variety of places. In the high frequency bands, there'll be quite random, there'll be sudden bursts and increases in level from lightning strikes all around the world. You'll hear as static, what's called static crashes. There'll be some man-made noise and other stuff, and on some of the high frequency bands a bit higher up you'll get noise from outer space. Jupiter adds its share around the 15-metre band and all sorts of things. So that's contributing to the background rubbish that we don't want to hear, the noise. Now, the stronger the signal, the cleaner it will sound. So when you're listening to an amateur talking from the other side of town, it will sound like he or she's in the room with you. It'll be nice and clear, there'll be hardly any background noise. Now, as the signal gets weaker, now the noise doesn't change, but the noise doesn't change, but the signal gets weaker. So as you're listening to a weaker and weaker fading signal, fading up and down from the other side of the world, the difference, the ratio between the signal and the noise becomes much smaller. The signal-to-noise ratio is getting poorer. And it's generally, you can express it in decibels, and we haven't covered dB yet, but you can come back to this if you like after that. So a very strong signal, the noise is very weak in comparison with the signal. It's a very big ratio, but a weak signal arriving at the terminals of the receiver, the signal-to-noise ratio is very poor, and it will sound noisy. You're starting to hear the background noise is getting demodulated, and you'll hear the noise. Now, why is this important? Well, it's important if we're receiving weak signals as to how our receiver performs, because we know in the receiver we've got that RF amplifier here. There's a filter as well, and I keep leaving out, mixer, and then into the IF system with the filter built in the detectors. Now, the problem is if we're dealing with very, very weak signals, when you start entering the receiver, the radio frequency amplifier and the filter in front of it and the mixer add noise. They're not perfect. If you soak them in liquid helium or something and make them very cold, they won't add much noise, but just the random motion of electrons in the system will add noise to your signal. And what that effectively does is it worsens the signal-to-noise ratio. So if we look at this point here, here's our wanted signal. It would have been shifted to some other frequency, the IF, but the noise has now come up. the gap between the signal and the noise is lessened. Now, if it's a very strong signal, that doesn't matter, because it's such a big difference anyway. If you make that worse by a bit, then you won't hear the difference. But if you're dealing with quite a weak signal, and you've got poor quality electronics in here, and especially in the front end of the receiver, then you may actually lose the signal altogether. A good quality receiver, you may be able to hear it, but a poor quality receiver, the noise has now come up. The noise that was already there has now increased so much by the noise added here that the signal's gone forever and you can't hear it. So that, now remember, the reason we put the RF amplifier in here in the first place was to just lift the signal up a bit, just to help the noise issue. You see, receivers generally have the radio frequency amplifier at the start is generally the lowest noise receiver. You try and have that as the lowest noise receiver, noise amplifier in the receiver, to lift the signal up a bit, just to get it started as it heads through the receiver. There's an oversimplification, but it's good enough for this. But that has to be made relatively low noise in receivers, because the reason for that is that this amplifier is dealing with a signal at the weakest it'll ever be. So any noise that's added there is very close to, in a weak signal, any noise that's added there, if you're not careful, will swamp the receiver. Further down the chain, the signal is so strong that if you add the same amount of noise down there, it will have hardly any effect. So that's why front-end receivers have to be quite low noise. And in VHF and UHF receivers especially, it becomes much more significant. I'll talk about that in a minute. Now, it's not nearly so much a problem in the lower high frequency bands like 80 and 40 meters, because there's so much atmospheric noise from static crashes and so on that it's not an issue. Any noise added by the receiver is just immaterial because the atmospheric noise is so high. And often, modern receivers, you have an option of switching the RF amplifier out. Now, why would you want to do that? Well, there are advantages that when you have amplification ahead of the mixer, if you start amplifying strong signals and the mixer has been hit by a variety of strong signals coming down the aerial, its performance can deteriorate. And I'll come on to that when we talk about intermod. So there can be advantages for removing the amplifier, and you do that in situations where the signal coming in from the aerial has got so much mad atmospheric noise added, there's no point in giving the signal a boost before it heads on its way, because there's so much noise anyway. When you're dealing with very weak signals at VHF, UHF and micro, getting up over 1,000 megahertz when people are bouncing signals off the moon and so on, or weak signals from trying to work DX, from one hilltop to another one miles away, the signals can be very weak. And people strive very hard to have very low noise amplifiers in their receivers. And one thing they'll often do is put an RF amplifier right up by the aerial. Now, the reason for doing that is that when you come down, when you've got your coaxial cable, your transmission line, which we're going to come on to, that could be many meters of coaxial cable in there, is that you lose signal as you go through a feed line. Now, that has the same effect as adding noise. It's the random motion of the electrons in the coaxial cable from heat will add noise to the signal as the signal weakens going down the coaxial cable. So the signal to noise ratio is at its best actually at the aerial terminals, and it deteriorates as it goes down the coaxial cable. That's not normally much of a problem at HF bands, but at VHF, UHF and microwave, that's quite critical where you might be dealing with very weak signals. So what people will do is they'll put an amplifier right up by the aerial. And that's the same with TV. If you're in a weak signal area and your TV receiver is a long way from the aerial and you want to put a booster amplifier in, you don't put it at the back of the TV set, because your signal's noisier there than what it is. All you're doing is just amplifying a noisy signal. If you can put the amplifier up at the aerial, and that's why they make them waterproof and you can have arrangements to feed the power up the aerial cable to them. So that's just a bit about signal to noise ratio. They try and have the amplifiers at the very start of the receiver as low noise as possible to you don't deteriorate the signal to noise ratio of the signal. And then all you end up doing is listening to noise coming out the other end rather than a clean signal. All right. Now, nearly finished. The other thing I wanted to talk about was direct digital synthesis. On the other one was digital signal processing. So these are non-examinable for the NZART question bank. But I think it's of interest because it brings the stuff we're talking about really well and truly into the 21st century. And this is all to do with the local oscillator. Remember the mixer? RF amp, which as we see can be optional. Front end filter. Off to the IF system. Now this local oscillator, that's where probably some of the biggest advances in the last 2 decades in commercial, receiving systems. Now, up until the 1970s, and currently with homemade gear, that local oscillator is an adjustable thing, and it's a inductor and capacitor combination and tune circuit built into an amplifier which is made to oscillate according to the setting of the tune circuit. And that produces the signal that's injected into the mixer. And we're talking radios like the FT101 and TS520 that you might come across on eBay or Trade Me. And they had a mechanical gearing arrangement and a scale, a dial system, coupled to the tuning capacitor inside. And you had to have quite a lot of fancy mechanical work to make it nice and stable and to gear it down so you could tune at a reasonable rate across the band. And they worked fine, and they produced a nice clean signal into the mixer. But to make it easier to have digital displays of the frequency you're operating on and for various other stability reasons, see the problem with those oscillators is what's called free running, and they can drift a bit. The stability can wander around a bit. As in the 70s and 80s, phased lock loop technology was introduced for the local oscillator. And you can read about it. I won't go into any great details because it's a subject on its own. But basically what was done is you had an oscillator that was running at the frequency you wanted, but it was controlled by a variable capacitance diode electrically to keep it on the right frequency. And what would happen is you had an arrangement where the tuning knob on your set was actually connected to some digital electronics which would shift that free running, it would take a sniff of that free running signal, oscillator, compare it to a fixed crystal oscillator reference, and then put an error signal back to the oscillator to keep it locked onto the frequency you wanted. It was called a phase lock loop. So it was sort of kind of comparing the oscillator to a reference according to the setting of the knob and keeping the local oscillator on frequency. And it worked reasonably well. It did have problems though. It tended to produce quite a noisy signal. The oscillator wasn't as clean as the free running one, and noise on your oscillator has the same effect as noise on your signal, and it can degrade, and there's other problems with it as well, but it could degrade your receiver performance. And then along in the late 80s and 90s came a newer system called DDS, direct digital synthesis. And that's kind of where we're at now, a mixture of phase lock loop and direct digital synthesis techniques, such that through digital electronics and number crunching, it's replaced by a box called a DDS system. And then you've got a microprocessor, CPU, central processing unit, MPU, whatever, basically a computer. And then you've got your knob attached to that, or a keypad for entering frequency, or you could have memories, or the knob now is just connected to an encoding system to tell this thing how fast it's going and which direction it's going to know if it's tuning up or down. And the microprocessor tells this unit here what frequency to inject. And this is done using a digital system where the signal is actually manufactured, if you like. If you look at the local oscillator signal going in, it's actually a sort of a stepwise construction of a sine wave, which is then cleaned up in some filtering to make it look like a sine wave, but it's actually mathematically created. And that's kind of the technology we're at the moment with modern radios, and it works very well. And it gives you that you don't have to have a sophisticated gearing arrangement and so on to a variable capacitor which can drift around. It allows microprocessor control, so you can have memory arrangements and so on, and allows it much easier to have the digital display of your receiver or what have you, showing you the frequency you're operating off. And in VHF sets, if you want to call it whatever the name of your local repeater is, you can actually tell the microprocessor through programming to just display the name of the repeater, not display the signal frequency. Yeah, but this stuff applies for when we come on to transmitters, when we refer back to it. And transmitters we use a local oscillator as well, and this would be reused in the transmitter as well. That's DDS, direct digital synthesis. It's really, I mean, that's just, there'll be a whole course in its own right. It's quite a complicated area, but just to give you a rough idea of what's going on the radio, it's mathematically doing the job of the local oscillator under microprocessor control, and that gives you a lot of flexibility. The last thing is DSP, death by abbreviation, to digital signal processing. And nearly all modern receivers and transceivers have this option. Very powerful system for getting around noise problems and actually doing the basic operations of the receiver. Digital signal processing is, we're not going to go into any details because this is a huge area in its own right. Basically what you do is, after the intermediate frequency, after the IF amplifier, the signal is actually analysed by a computer-based system where whatever signal coming out of the intermediate frequency amplifier, it can be done at sound after it's been converted to audio by the demodulator in an SSB system or something like that. But in a nutshell, what the radio is now doing is it's same system for encoding information onto a compact disc. Is at regular points, regular time intervals, the system takes a measurement of the amplitude, the voltage of the signal, and converts it to a digit. It digitizes it. It converts it to a digital number, and generally done in binary, which is ones and noughts, which computers can handle. So it converts it to a fast stream of binary numbers. Once you've done that, you've now got the ability for a computer to analyze it, and it can do very clever things. It can look for, maybe you've got an annoying whistle, you know, beep, going in the background from another signal nearby, often called a heterodyne or a whistle. It can look for a regular repeating number pattern and remove it, subtract it from the signal, and you push the notch filter function, it's called, bang, it's gone. It can do any other sort of noise, you know, regular. See, the modulation is going to be a fairly random sort of phenomenon, but anything that's sort of regularly repeating itself and being a pain in the background in sort of in a noise fashion, it can get rid of that. So I probably haven't quite explained that well, but as I said, I don't want to get stuck into DSP. But just to suffice to say that using digital techniques, turning your signal into streams of ones and noughts and analysing it can actually subtract off it annoying signals, then convert it back to sound again. So it's a very clever trick. And the last thing, so that's the first thing that digital signal processing was really used for was getting rid of noise and interference problems. You know, it's stuff on your signal that you don't want to listen to. The latest thing that DSP is doing is in sets like FT1000s and so on, which is a contemporary, you know, high-end radio made by Yaesu and ICOM 756s and things like that, is that, remember we've got the front, we've got the mixer, we won't draw here's our DDS system here, and then we go onto those filters, we still have those, and then IFM. What they'll often do is then convert it, actually go back to double conversion, but for other reasons, convert the IF down to a lower signal, a lower frequency that can be handled easily by a digital computer system. The IF frequency actually in modern radios might be quite high, around 70 megahertz. They do that for various reasons. And then from then on, we're in the digital world. You enter the DSP, so it can convert it down to quite a low IF, maybe say like 20 kilohertz. In the old days that was done to get the selectivity. Well, no, that's not a problem nowadays. You've still got that selectivity here. What they do is they convert it down to a lower frequency that a microprocessor system can handle, can sample and digitize quite happily. And what's done now, this is a spooky thing, is that often the detection, the demodulation, the removing of an SSB signal, converting it, getting the sound out of it, or turning a pulsed carrier on and off into beeps, beeps and parps for listening to Morse code, or for detecting, frequency demodulating or discriminating FM. It's no longer done by, product detectors and carrier insertion oscillators and so on. A lot of that technology is actually done digitally. So a lot of what we've taught earlier is still relevant, a lot of radio gear, but increasingly nowadays that function of the radio, if you like, the back end of the radio, is actually being done in the digital world by digital signal processing, and I think we'll find probably as the time marches on, perhaps more of it will be done further back, and this is into the world of the personal computer with modern PCs being very fast and can do incredible tasks quite quickly. This can actually be done on the sound card of a PC. You can actually take the sound out of your audio jack, out of your radio, and feed it into a sound card and run the appropriate software for getting rid of noise and doing DSP that way. And the other trick is with certain data modes, the information can be extracted off the signal using digital signal processing in the sound card of your personal computer. And it's become a very powerful tool nowadays for people experimenting with that sort of thing. So anyway, so that's. So just before I show you some examples of some receivers, let's see which pen's still working. The last thing I want to mention is intermod. Once again, this is not in the NZART exam, but you'll hear this technique mentioned. There's a lot of things that can cause problems in receivers, and this is one of them. And it's a phenomenon that's related to that frequency 1, frequency 2 combination that takes place in mixers. Remember, we've got a bandpass filter, just allowing the frequency, the amateur band of interest to pass through, amplifier, mixer. This pen's recovered off to the IFM local oscillator. These amplifiers aren't perfect, they add a bit of noise. The other thing they do is that, and the mixer as well actually, the mixer adds a bit of noise too, is that signals can combine in them in other ways as well and create new signals. And that's not normally a problem until they get quite strong signals passing into them. And it's related to signals that we don't want to receive or we're not tuned to. So we might be tuned to, actually, let's just give an example. Let's say we've got a very strong signal coming in here on 3.60 megahertz, a very strong signal on 3.65 megahertz coming into our receiver. These two signals here. Might be a couple of local amateurs, one on 3.6, another one on 3.65. Not an entirely reasonable thing to happen. Now, here we go, here's my example. What can happen is, well, in theory, if these are the only two signals coming down the antenna, when we tune around on our receiver, they should be the only two signals we receive. We hear nothing until we hit 3.6 and we hear that signal. Keep tuning up, 3.65, you hear the other signal. Keep tuning away, you can't over the band, 3.5 to 3.9. As we vary the local oscillator to receive those signals, that's all we should receive. But unfortunately, it's not as simple as that. We get this thing called intermodulation. And it's when very strong signals pass through a system like this, they interact and create new signals. It happens in the single sideband transmitters, and we're going to talk about that. It's called splatter when we come on to transmitters. It's a nasty phenomenon. And it's called intermodulation or intermod. It's also a major problem on amateur radio, on repeater sites. We've got lots of strong signals in close proximity. What happens is these things here can combine such that we call that one F1. Now this has nothing to do with what the local oscillator is. We'll just call this frequency 1, frequency 2, is that we can get new things formed. We can get two times F1 plus and minus 3 times F2, or we can get 2 times F2 plus and minus 3 times F1. Now this happens all the time in this. Now this is happening all the time, but fortunately, normally, in a well-designed receiver, the strength of these new signals created are so weak they don't cause a problem, or they're not actually appearing at all. The problem is, if our poor old front end, the filter, not normally much of a problem, but certainly the amplifier and the mixer, if we've got very, very strong signals coming into our receiver, we get new signals created coming out of here that don't exist on the aerial. They've just been manufactured out of the blue by flaws in the receiver and the mixer. And generally it's when we call them, if they're not very well designed or just built on the cheap, this will happen. So if you do the maths for 3.6 and 3.65, well, just forget the formulae. If we've got very, very strong signals on those two frequencies coming in, just for example's sake, and our receiver is not particularly well designed, okay, this combination will create two new signals out of the blue on 3.75 and, I had to work out the math, 3.5. So you could actually do this on older radios, especially things like FT101s, the Yaesu FT101s from the 70s, not picking on it in particular, but its front end, especially the early ones, was not particularly robust. In other words, it couldn't cope with strong signals very well. And you could do this as a demonstration in the class. You put the 3.6 and 3.65 megahertz signals into the receiver, just manufacture them with signal generators and have them reasonably strong. And sure enough, as you tuned around on your receiver, yes, you'd hear the signal at 3.6 and hear it at 3.65. Tune down to 3.5, you could hear it as well. Tune up to 3.75, you could hear it. So the radio is actually creating new signals just because of a relatively poor design in here, in the front end. And that's called intermodulation, which can be a real problem. Modern receivers are designed, the mixer and the amplifiers quite well, especially the high-end stuff, the really high-quality stuff. They put a lot of design work into the front end of the receiver to get around that problem, because that can be very significant. And you do see it if you're, say there's a contest on the amateur bands, and you're working on the 20-meter band, 14 to 14.3, and around the 14.2, 14.25, and a bit below, maybe 14.15, right up to 14.25 and beyond. And there's a whole lot of very strong signals on the amateur band, people calling all around the place, maybe stronger than that. If your front-end receiver is not very well designed, if you then do number analysis of all those signals, you then suddenly get all these extra signals created. And when you're getting, what happens is, say, in this example here, say it's a conversation taking place at that and another one at that, what you'll end up at these frequencies here is sound like an awful mess of the speech from those two. And that's what would happen on, say, the 20-meter band. Say running from 14.0 to 14.35. If there's a whole lot of strong signals around, then all of a sudden these other signals will start appearing. And all it is just signals created in the front end of your receiver because of poor receiver design, and it can actually make your whole receiver unusable under those conditions. Fine if there's only a few weak signals around or medium signals on the band, but if there's a lot of strong signals by half the world calling CQ in a competition, and if they're very strong, especially local stuff as well, you'll get all these extra signals there, and you'll try and tune into them and can't resolve them because they're actually a mixture of several signals, and it's horribly distorted and doesn't sound very nice. And it's a real limiter of receiver performance under strong signal conditions. And that's intermod, and that takes place. It's a creation of new signals in the front end of your receiver, and they're definitely not wanted. Can you do something about it? Yes, you can, through better design of the front end of the receiver. And that was why I said on the lower amateur bands where signals are very noisy, that this amplifier has very little to contribute, that you can actually switch it out. So if you're in a contest on the 80-meter band, a lot of strong signals around, and if you can switch out the front end amplifier, you'll suddenly find that all those stray signals will vanish. You'll just be back to the few signals that you actually want. It's an interesting subject, and And that's why you find too on radios that they seemingly do the ridiculous sometimes, that you can actually switch in and between the aerial and here, an attenuator. The symbol for it is kind of a resistor thing. You can actually switch in a resistor arrangement to cut back the signal strength. Yes, it will add noise to this. It will degrade the signal to noise ratio of your receiver. But if most of the signals around are very strong, and all you want to do is hear strong signals during the contest for most of the time, you can help stop that intermod from happening by switching in the attenuator into your receiver, and it will drop down the strength of everything, and it will tend to make those intermod products just, drop down much further, or even vanish altogether. When you're getting intermod taking place, just a small, if you can just reduce the strength of the whole lot just a bit, you'll drop the rest of it a bit times 3. You actually have a much bigger, so that's why it's an advantage sometimes, although some of the weak signals might vanish, but at least you can make life a lot more easier for yourself. I hope I haven't confused you too much. Right, I'll just finish with, to show you the inside of a New Zealand-made land mobile repeater receiver, but it just shows you a few of the bits that you might find inside a Right, here we have a Tate T200. I've showed it a few times before to show you bits and pieces in electronics, but it's not really, much like, physically the receivers we use in amateur radio, but really the principles, the functioning of it is pretty much the same, and it's all nicely open, so we can talk a bit about it. Here's the front panel of it, upside down. There you go. It says it works on A band, which in New Zealand is about 82 to 88 megahertz. It's designed to work over that range depending upon where you set it. But there's a component side of the circuit board. Here's the aerial connector at the back. These connections here feed the power in and so on and take the sound out that we receive. Here's the coaxial cable coming in from the receiver. Now what it is, these cans here are, we've mentioned this before, that's the first filter in the front end. Here's the radio frequency amplifier. Here's some more filtering. And here's the mixer. It's a field effect transistor mixer. And then into the intermediate frequency filter. That's the IF filter running around about 10.7 megahertz, setting the selectivity of the receiver. So this arrangement's giving the image rejection. That's the mixing. This is giving you the selectivity, and then it comes out of the air through that field effect transistor. These 3 transistors are the IF amplifier, and then the AM detector is around here. It's an AM receiver, and here's the sound amplifier here. Now the local oscillator is along this way here. It uses a quartz crystal because it only has to work on one signal frequency. You can do that in receivers. If you only want to work on one fixed frequency forever and a day, you can keep it nice and stable without having to retune all the time. Use a quartz crystal oscillator arrangement. That's the local oscillator chain here. So that's feeding frequency 2, if you like, into the mixer, and frequency 1's coming down through here, and then the sum and difference hit the filter, but only one of them will be the one we want, so that's 10.7 will be the difference probably, and the sum will be something much higher, so it won't get through that, and then on it goes through the rest of the receiver. Right, we'll just take you next door and just show you a sideband receiver in operation. Right, we just wandered into our radio room here at the Civil Defence Rooms. So we see a number of operating positions here with various VHF and UHF radios. And what we're interested in here is our high frequency amateur transceiver, which is used primarily for single sideband voice communications. And if you listen here, we're tuned to 3.64 megahertz lower sideband. It's operating on lower sideband at present, and you can just hear there it's a bit noisy. You can hear a conversation taking place on single sideband. The band's a little bit noisy at the moment. I'll just stop recording and see if I can find a slightly louder conversation to listen to a stronger one. You can hear a conversation taking place on 3.6 megahertz in the 80 meter band on lower sideband. Now listen, if we switch to AM, almost impossible to resolve, and we used to call that duck talk. That's without carrier re-injection. All we're hearing now is just the signals that make up the single sideband signal sort of combining with itself, and you don't get any sense out of it. Now if we tune it off frequency, it has the effect of the signal we want moving away from the intermediate frequency and out of the pass band of the IF filter, so the signal will get weaker and vanish. Now it's gone. We're only just 3 3/3 of a kilohertz away. It's vanished, and we tune back and it reappears. Now with single sideband, as we move away from the signal coming out of the IF amplifier system into the product detector, as we tune away from it, it actually moves away from our carrier insertion oscillator or BFO frequency. So the speech gets shifted in frequency as well, and you'll hear it having this effect here. So we've shifted the whole range of frequencies up. If we tune the other way, it goes down. So it's not until we got it tuned on the correct frequency of single sideband that all the tones in the voice are the correct frequency. You get that monkey chatter effect. Now with AM, you don't have that problem. So we're just tuned there we go, there's New Zealand's national program, 567 kilohertz from over near Wellington. And as we tune off, there's no pitch change because the carrier is supplied, if you like, by the transmitting station, so it is not changing in frequency. The carriers come along with the signal, but as you tune away, we start moving outside the IF filter pass band. The signal gets noisier and weaker, and eventually vanishes. It's not till we tune back to 567 that everything comes right. But we'll have a look at an FM. Actually, we'll just quickly find some Morse code to listen to before we finish. There we go, Morse code signal conversation taking place on the 40 meter band, 7 megahertz. As we tune our local oscillator, the frequency we're shifting it to at the IF is changing. So the relationship between our signal IF and the BFO's fixed is changing, so the pitch changes. There you go. This is an ICOM 2000. It's a 2 meter VHF FM amateur band transceiver. Now we can't hear anything coming out of it, even if we turn the volume up, because we get that horrible squelch effect, FM effect. If we open the squelch here, that busy light comes on. That's rather fatiguing. I said that's rather fatiguing to listen to all day. So when there's no signal present, you've just got noise coming out of the frequency demodulator or discriminator. The set automatically detects that noise and shuts the works down. If we trigger the local repeater, I'll just put a call out to say I'm listening. ZL2 Tango Whiskey testing on 14695. So you can see when the carrier is coming back.
ZL2 Tango Whiskey,
I've just been called.
Hi there, Stuart. Yeah, if you could give me a ring in about 10 minutes, that would be great.
I'll just answer, that's Helen Harris. ZL2HH, ZL2TW. Roger Helen, will do that when I get home. You just caught me recording actually for my classes, so I'm recording the conversation. I was showing an FM set in operation. So thanks for that. Okay, I'll give you a shout in about 10 minutes. ZL2HH, ZL2TW out.
Thanks, Stuart. ZL2HH mobile
I was using the microphone there. See the bar graph shows the signal strength. Very strong signal. My carrier goes. There you go. So an FM receiver. When there's a good signal there, it all switched on, opened the gate or the mute or the squelch, and we could hear what was going on, then shut down. Now I just want to show you a set over here. This is a commercial FM VHF set, and what they've done here is they're not displaying any frequency information. Remember I said we've got a microprocessor controlling the local oscillator. you can actually put labels on the channels that suit you. So this is the Emergency Operations Centre channel 11, channel 12 and so on. You can see the channel numbers. And it's arranged in groups. So we go through another group, there's the Marine channels from MAR, Department of Conservation channels, Marlborough Lions, channel 1, Carter Holt Harveys, so various other, and then within a group you can have different channel arrangements again. So you can see the flexibility here. The operators here aren't really interested in what frequency they're operating on in civil defence. They just want to have fixed channels to talk to particular people around the place. Much easier just to program it up with various names. It's called alphanumeric labelling, alphanumeric, so alphabet and numbers. So that's the flexibility you get with a microprocessor controlling it. Now if you come here to this Marine set, this is running about 156 to 160 megahertz on the international Marine VHF frequencies. It's another FM one there, so you've got the squelch arrangement. And on Marine channels, Marine operators aren't really interested in what frequency they're operating on. They've got about 80 odd channels that are assigned to fixed frequencies. And they just stick to 16 as international distress and marine calling frequency on VHF. So it's just, so when you're talking about Marine channel 16 or channel 1 or 63 or whatever, everyone knows what each one is talking about. It's only the technical people who service the gear or make aerials or tune repeaters on hilltops for marine use have to know what frequency it's operating on. Just come around, there's a few more of those VHF ones. And just over here is an older fixed channel high frequency sideband set used for New Zealand civil defence frequencies for longer range stuff around the country. And they use crystal control for the local oscillator to select the frequency you want to operate on. There's a number of crystals inside there, that quartz crystals you select, and it has separate filters for each frequency you want for the front end filters, which are selected as well while you switch that. So I think that just gives an example of some of the equipment we have around on high frequency and VHF and so on.